Hey everyone, so today we're diving into something that sounds complicated but is actually super useful, partial derivatives. Now don't panic when you hear the word derivative. I know the word alone gives flashbacks to sleepless calculus nights, but trust me, once you get the idea, it's pretty intuitive. By the end of this video, you'll understand what partial derivatives are, how to calculate them, and where engineers actually use them in the real world. What is partial derivatives? Okay, let's start simple. A partial derivative basically measures how a function changes when one variable changes, while keeping the other variables constant. Think of it like standing on a hill. If you walk straight east or west, you'll feel the slope going one way. That's the partial derivative with respect to x. If you walk north or south, that's the slope in the y direction. So partial derivatives are like checking how steep the hill is in one direction at a time. In engineering, we use this to analyze systems that depend on multiple factors. For example, how temperature changes with position and time, or how stress changes with force and material thickness. An ordinary derivative deals with a function that depends on just one variable like y equals x squared. It tells us how y changes when x changes. But in partial derivative, we have two or more variables like z equals x squared plus y squared. Here, z depends on both x and y, so we can find how z changes when we vary x while keeping y fixed, and vice versa. So, ordinary derivative is one variable and one direction, while partial derivative has multiple variables, one direction at a time. It's like comparing walking on a straight hallway versus walking on a hill in a park. There are multiple directions to choose from. Alright, now the fun part. We'll go through three problems together and I'll explain each one in words so you can follow easily. So, for example 1, f x y equals x squared y cubed. Let's find the partial derivatives with respect to x and y. So here, fxy is a function of two variables, x and y. If we take the partial derivatives with respect to x, we treat y as if it's a constant number. That means we only differentiate the x part, and we get df dx equals 2x y cubed. That's because x squared, when differentiated, becomes 2x. In words, for every small change in x, the function changes twice x times y cubed. Now, for y, we do the opposite. Treat x as constant. The answer for df dy is 3x squared y squared. That's because the differentiation of y cubed equals to 3y squared. So here, for every small change in y, the function changes 3 times x squared times y squared. That's all. For example 2, let's take the partial derivatives again. First, with respect to x. Here, y plus 2 is constant, so we only differentiate x squared minus 1. That gives us df dx equals to 2x bracket y plus 2. That means if x changes a bit, the slope of f depends on both x and the y value. So now, for y, we treat x squared minus 1 as constant and differentiate y plus 2, which becomes 1. So the answer for df dy equals x squared minus 1. That means for every small increase in y, the function increases by x squared minus 1. This is a great example to see that sometimes the derivative doesn't depend on the other variable. Now, example 3. If we want to find df dx, x is kept constant, so we only differentiate y. The differentiation of e power y is equals to y e power y. So the answer gives us df dx equals y e power xy. And for df dy, y is constant this time, so we just need to differentiate e power x. The differentiation of e power x equals to x e power x. So the answer is x e power xy. Now you might be thinking, okay, that's cool and all, but When would I ever use this outside a math exam? Here's the thing. Partial derivatives show up everywhere in engineering. Take heat transfer, for example. The temperature in a metal plate might depend on x, y, and time t. The partial derivative dt dx tells us how temperature changes as we move horizontally. Dt dy tells us how it changes vertically. Engineers use this to design cooling systems for engines, microchips, or even your gaming laptop that sounds like a jet engine when you play for a long time. Partial derivatives also appear in stress analysis, fluid dynamics, and control systems. Basically, if it moves or bends or heats up, there's a partial derivative behind it. So why are they important? Because real engineering problems are rarely one-dimensional. Everything depends on something else. Partial derivatives helps us model how systems respond to changes, optimize performance, predict behavior under different conditions. Without them, we'd be guessing. And you don't really want your bridges, planes, or engines designed by guesswork. In short, partial derivatives are like the fine-tuning knobs of engineering math. They help us understand exactly how each variable affects the system one at a time. So, to wrap up, partial derivatives are just normal derivatives, but with friends. They help us study how functions change in one direction while keeping others fixed. And they are super useful in real-world engineering. So next time you see a curly D symbol, don't panic. Just remember, it's a slope in one direction at a time. And hey, if you survive calculus, you can survive anything. Thanks for watching, and may your slopes always be positive.